Hello, this is my first development log of the Tython programming language compiler, even though I've technically already started on it. We'll just navigate to the directory it's in. Here, make sure I'm up to date with the latest version. This looks good. So here's the README file. So basically the idea with Tython is that it's the compiler. It's written in Python, but the language itself is the opposite of Python. I mean, besides the obvious, Tython will be compiled, unlike Python, which is only superficially compiled at best. It's based on the TI-84 basic programming language, which is used to write simple programs for the TI-84 plus CE, like TI-84 calculator series. And I've actually spent a lot of time programming in TI Basic, which is why I wanted to port it over to a real computer language instead of just being stuck on TI plus CE emulators. This language has a bunch of features that are almost like never found anymore in programming languages. Specifically, several things. It doesn't have functions. It doesn't have objects. It doesn't have any type of flow control. Any sort of like these things you would consider to be like basic ideas. They're strictly not necessary, and there's something beautiful about not having these like things, like structures in place to make it easier on you. It's closer, I guess, in some sense to assembly, which would kind of make it, I guess, easier to compile. Tython has no features that are redundant, right? So every single command, every single feature of Tython has an explicit purpose and cannot be replaced by any other object. Oh yeah, I forgot to mention, it also doesn't have any loops. So no while loops, no for loops. Actually, the only thing it does have, no functions, no while loops, no objects, right? Just labels and go-to statements. My favorite. Okay, yes, the Zen. Less features is more important than readability. Variables are one letter long. This is something I borrowed from the graphing calculator, but you can add a number to the end, so it's not just 26 variables. You can have 572 variables, apparently. And this is wrong because this includes the fact that you can have uppercase and lowercase versions. I think in this language, all uppercase and lowercase everything will be treated the same. It's not case sensitive. When it's compiled, it'll just assume everything's uppercase. Yes, all variables have an implicit type. This is just like Fortran. I think it's kind of cool. So here's your types. There's integers, there's real numbers, because math often requires some sort of float, and there's characters in order to implement strings and hello world. Variables I, J, K, L, M, and N are integers. This is borrowed from Fortran. Otherwise, it is a real type. This just makes sense. In math, I, J, K, L, M, N are assumed sort of to be integer variables. So it makes sense for them to be the same way in code. You can change the type of any of these variables. Like if you don't have enough integers, you can just make one of the other variables an integer if you want. I don't care, but you have to explicitly say so, or else we'll just assume the other There's no Boolean type because that's just an integer, and I hate the fact that Booleans are just integers. And okay, this is wrong. It's actually an at sign now because at looks like an A, stands for array or vector. Obviously, blah blah blah. List or index with square brackets. There are no loops, but there are goto statements, right? There are no functions, only programs and labels. Like labels and gotos literally fulfill the same role as loops and functions. So why do you have both? Who knows? The calculator language doesn't have any functions. Well, it does have loops, but has no functions. And I went a step further, I guess, and got rid of loops entirely. You can't. There's a way to kind of call functions, and that by calling other programs, and where each program is considered to be a function, in a sense. And you can sort of get away with recursion in this case. And I hate recursion with every fiber of my being. So I'm going to do what I can to make sure that recursion is not possible. You can add as many spaces as you want between your words. I don't care. You can format it however the hell you want. If statements are paired with an end keyword, because there's no scopes and no curly. I mean, there are scopes, but there's no curly braces. Yes, variables. If you assign x equal to some number in one program and you invoke another program, the value for x will remain even in the other program's execution. So it's like kind of like assembly in that way. Yes, and it's Renegade. Tython is a programming language for the rebels. Here's an example of some Tython code. You need to declare the name of the program. This is just make it easier on everyone involved. So these would be like commands. So this would just get like what, get an input and insert it into A. These are all just stolen, by the way, from graphing calculator. Yeah, this is the quadratic formula. Right? The comments are delimited by these hashtags. Yeah, you can set this O, which is obviously an implicit real type, and all these are implicit reals. Just, you know, standard stuff. Plus or minus 4a, plus or minus square root of b squared minus 4ac, yes. And you display both of them. Here's like a banking system, which just kind of stores like money in like a simple graphical user interface. The Fibonacci sequence is a classic. This one uses arrays. So we use this @ sign to denote an array with data type int32. This dim I is stolen from the way the graphing calculator resizes arrays. So when you dim I paired with this assignment operator will change the size of I. Like in this case, it will increase or decrease the size of I to 20, and it will pad with zeros if you're increasing it. So we set the first two elements of I, 0 index by the way. We set the first two elements of I, and then we iterate over the rest using these labels, this iterator, and sort of this goto statement. And we just do the Fibonacci sequence. So we the ith term is the previous, and you know what I mean. Okay. Oops. I changed something? Oh yeah, I did. Okay. Here, this is the my working compiler as of now. So this is the great token type and new enum. There's no enums in Python. So this is what we can get, but it gives you the special thing of, instead of forcing you to use integers in your enums to differentiate between the different enums, you can actually give them actual values, which sort of to me confuses the concept of an enum, but whatever. But here I actually stored a regex strings that the compiler uses to match these patterns. So obviously all these data types, their pattern is themselves. These mathematical operators, the pattern is themselves as well, except you have to put this backslash because regex sometimes uses these symbols as control sequences, so you're gonna have to tell regex, no, I literally mean, you know, this parenthesis instead of a scoping. If, then, else, and end, these are your conditional statements, right? I'm not so mean as to remove conditionals. That would actually probably make it not Turing complete anymore if I remove those. So unfortunately, these have to stay. Flow control, so we have label and go to, no functions, obviously. No loops. Comparison operators, standard stuff, borrowed from Python. These are sort of the program control. These are the variable literals, so anything bounded by quotation marks is considered to be a string literal. Anything that is a digit, I need to include explicitly no dots in there. Integer literal. A float literal is numbers with a dot at the end somewhere, or in the middle. A hex literal has the prefix 0x and then some non-zero number of characters or digits, but the characters are strictly between A and F. A binary literal, so these 0x and 0b prefixes I stole from Python. I'm just a big stealer. The zeros and ones, but at least one of these. You can't just have 0b nothing. Variables obviously are at least one character and optionally a number as well. An array variable is the same as a variable, but it has this ampersand here. Display string, these are just like display things to the screen. I have some basic math functions, so these will just come shipped with the language, just like the graphing calculator, I guess. Sine, cosine, tan, cotangent, secant, cosecant. The dim function to and these are structure tokens. So the way the compiler works is when the lexer goes through and sort of analyzes the program and creates these tokens, there's some important structure things it needs to remember, including the existence of commas, expressions, line breaks, where the line breaks are, and functions, so where functions are, like the names of functions. And a token itself, these are just the types of tokens. The token itself has a type and it has a value. And the value just remembers sort of, if the token is like an integer, it remembers which specific integer was typed. Here's a simple repr function, you know, classic. Here's the lexer object. I override the, it's more of like a namespace, I guess, because I'm using just class methods, but we override the call function, which allows us to call the object directly, and it will perform all the steps you need. There are 3 steps in the lexer. A lexer is responsible for taking the raw text input and generating a list of tokens, which are more easily digested by the following programs, you know. And it also makes it, like, you know, possible to look for patterns and look for syntax errors and looks for, you know, all these things. So the first step in a lexer is lexical analysis. And what this does is it literally goes through the raw text and it tries to, you know, replace all the text with tokens as to its best of its ability. It probably the resulting list of tokens very well could be wrong, very well could be, you know, not a program, or you know, otherwise illegal. But this is not its job. Its job is just to try to create something, and if it can't create it, then yeah, throw an error. So here's how it works. We store kind of buffers, which are substrings of the text that might become tokens, and we just crawl through the text, and we just we check for different types of patterns in the text. So spaces, if there's a space in the text, then that marks the end of a buffer, right? Because no buffer can contain a space unless it's a string literal, which is why we check if it's also not in a string literal, right? So no sort of substring that could become a token has a space in it. Same with the open parentheses. If we detect one of these, then there's a good chance that the thing that came before the open parentheses is meant to be its own token, because there's no token with a parentheses in the middle of it, or really in the beginning of it. So that's why we just append the parentheses itself. We check if there was something behind it and add it if there was. Same with the close parentheses. The comma is handled similarly. This is kind of interesting. The quotation mark is similar to the parentheses in that, and if you open a quotation mark, it probably means that the thing before it, there's a token before the quotation mark that we need to check for, right? And if there's a quotation mark and we're in a string literal, then we want to close that string literal. All these little things, right? New lines. So in Python, all new lines are \n, even though on this operating system it's \r and \n, I think. So means it's a register. Escape. Oh, what's it called? It's a typewriter thing. It's just a Windows. But in Python, when it reads text and it finds a line break, it will always write \n because it's nice to us, and it confuses language. Yeah, and then we go through every single buffer and try to assign a token. So, right, you'll notice like my style of Python is very, very industrial. It's like I write very industrial Python. So it's not just a variable, right? It has a compiler annotations. So this gives the compiler, it's called a compiler. It gives the text editor, in my case Vim, a hint about what type this variable is supposed to be. In this case, it's optionally a token type, which means it could also be none. Some text editors, if you hover over this variable, it will tell you like, oh, it's a token type or none. And it will give you suggestions based on that, right? Like for example, I know this will always be a token type, so I can just give it a compiler hint to hint that this thing is a token, because in Python, variables can take on any type that's required of them. So we do full match. So we check against the entire string whether or not it fits into any of these patterns. If you look up here, I use this unique decorator on the token type, which basically just ensures that, you know, these are all different regex. Not really, but in spirit. So there shouldn't be any issues with the full match. And if we are unable to match a pattern, then we raise a runtime error, which is the aforementioned yelling. And then we create a list of tokens. Very simple, right? Okay. Oops. So this is the output. So here's the buffers. It broke down. I'll show you. I think it's running hello.ty. So this is the program that is being ran. And here's the, God damn it. It's fucking broken. Nope. Anyways, you saw the program. So it's, the buffers are here. So we have program, then a string literal hello world. We tracked char8, this variable, this equals, this comma, you know, yada, 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 yada. Interestingly, it's unable to match token world. That makes, wait, why is this its own thing? What happened to hello? Oh, I know what happened. It found this comma in hello world and decided, you know what? That's probably a comma in a function scope, and got confused. That's nice. Okay. Where is it? Here. We need to make sure that we are not in a string literal. Okay. Okay, now it works. Yay. Yeah, so we have this buffer here. It ignores this comma. Thank goodness. That would have been a disaster. And it gives them their tokens. So the program is a program token. Hello, this, you know, name of the program is a string literal technically, so it will give that a string literal name. This array variable is given an array variable token. This hello world string literal, you know, all these other things. So the variable I, this is given in a variable literal. Right now I don't care which specific type this variable is. That's more of the job of the next part of the lecture, which I think is semantic analysis, which basically just looks through the tokens and says, well, is this I? Does it have a, you know, a data type token before it? In which case, like, we'll, you know, or if it doesn't, then we use this implicit type, whatever. An assignment token, etc. Plus token. It all seems to be working, right? Great. So yeah, it's not needed anymore. I thought I was going to use it, but nope. Here's the parsing. This is an argument parsing, not a compiler parsing. Which basically just does this. It gives us this. This is just a standard Python thing. It gives us a very nice sort of help. Like if you typed in something wrong, it makes sure you typed in the command correctly. I have an override right now that basically just defaults like these arguments, but in the actual compiler, it will not default the input file to anything. You have to give it an input file, otherwise the argument parser will yell at you. Right, and it gives you this like beautifully formatted thing. I think it's nice. Anyways, that's where I currently am. Maybe I'll try to develop as well on screen, but I'm kind of slow. Let's see how it works out. Great.